Okay, Calc 2, Lecture 6, and that is work. I guess most of you have taken Physics 1, and that is mechanics. And work is defined as force times displacement. Well, that's the simplest way to say it. But technically, it is force as a vector dot displacement as a vector, which that you will see in Calc 3. But for us, let's assume that the force and the x are in the same direction. So, or the same sense, let's say. So what will be F times x? F as just the magnitude of F, the force, and x just the magnitude of displacement. Now, to find a quantity which is defined as, it is related to some other things, so you have a formula for that. Remember, what I did was I said you have to find differential of that. So, for example, for work, I should find differential of work and integrate that differential to get work. So, if I find this, if I'm able to find this, then integrating that will give me work. Now, this work is F times x. So, I might have this situation. Work is F times dx. So it might be formulated the way that the increment is dx. Or it might be df times x. In both cases, you will end up with some dx. So you have to integrate over like a distance. There are situations that you might integrate over force, but for us it is just distance. So let me give you examples of each case. In fact, I will give you 2 examples, one for each case. And the rest of them I will discuss in the office hours. So let's take this f times dx. So example for this one. Okay, the simplest example is this. So if I have a say object connected to the wall, and I'm just pulling this thing F, and this is X. Sorry, this is K. The spring has constant K, spring constant. And it moves X. Okay, so what is F? If I pull a spring, say, just pull it down, and it moves distance X, so the tip moves distance X, okay. Then by Hooke's law, if the spring stays in elastic condition, it doesn't become plastic. Plastic means when you just go too far and just it collapses, and so it's no more spring. But if it stays in that elastic situation, then this is what happens. This is the relationship between, so F is some constant time x. Okay. And that's the spring constant. If you buy spring, I guess some commercial one, it should be written somewhere that the spring constant is this. Okay, so this force itself is a function of x, right? So that force is a function of x, and you need more force to pull it. So you just imagine you're pulling it and it goes a distance x. That force is changing. So in this situation, work is F dx and the work itself is kx. Okay, the W is kx, force is kx. So W is from x0, say, to x1. Suppose it starts somewhere at x0 and goes to x1. Kx dx. Okay, so that is 1/2 kx squared from x0 to x1. It's very simple, just fine. So that is when I formulated this in this form. It is in fact f times dx. Well, this example, this is perhaps the simplest example, and you might have seen this in your physics, that they write this as 1/2 kx squared, the work. And maybe they have discussed this in physics and why it is 1/2 kx squared, but you can see why it is 1/2 kx squared, where the 1/2 comes from, because that's an integral. It is not fx anymore, because that function f changes with x. F is not fixed. So because it changes, you cannot just write kx times x, kx squared. Maybe you had this question when you were studying physics, why is not simply kx squared? Because of this, because that function, that force, which is a function of x, changes with x. So you now know why it is 1/2 kx squared, because of this integral. You are finding an integral. Okay, the other one is a little bit, the example for the other one is kind of, sometimes I don't know why some students get confused. Now, the example for this one. Well, the best example is an example of a tank, a water tank, which is in certain shape. So it can be a cylindrical, it can be a cone. Well, so let's say we have a water tank of this shape, inverted cone. So this water tank has certain, say, radius here, and it has certain height. And it might be full, or it might be full up to some point. Okay, and we have a pump somewhere up here. So the pump is pumping water up. Now, well, this pump should be down here anyway. So we want to see what the work of that pump is. So what is it doing? The pump is, in fact, it's like you can have, I don't know how to say that, like some, something like so like say, take like a glass of water, say, just something small, say, and you use that glass of water, say, to, you pour the glass and you fill the glass with water and up. You fill the glass up, 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 up. So you can use something larger to do that, but anyway, what you are doing, you are moving a small portion of this water. So you take that small portion. This small portion has weight, and you pull it up, so you are going against this weight, which is some m times g, say, and you move it up some distance and throw it away, right? So you take a small portion of this thing, say like this cube, you move it up and up. So each portion has some mass, and mass gives you weight, and so since you are pulling this, so you are going against its weight, so the force that is doing some work is in fact the force of your hand, which is just pulling it up, and you move it, say, x distance, x, up, and throw it away. Okay? Well, you might say, why not using something else like y? Well, maybe I should use y because in this direction we usually use y. So let's say we move it y distance. So this is your force. So this is your F, dF in fact. So your dF is small object with certain mass. So this has mg. In fact, the g is constant, so it is dm times g, right? That's a small portion, very small. So that is like infinitesimal mass, right? That's infinitesimal mass. And the force applied here, this force is in fact the same thing, dm times g. And this force moves x distance, right? So the dw in this case will be df times x is in fact this thing, dm g times x. Okay? But what is dm? dm is that's mass of an object, physical object. So you can write this dm as some density times volume. So this is in fact the dm is some density times volume, right? Since it is infinitesimal, in fact its volume is small. Density, well, it can be anything. If it is just heavy, very heavy, say liquid, then this doesn't change, but this changes. So I can write this here again. So I can write here instead rho g dv times x. So what, say, a physicist should do here is finding this dv, finding the differential of volume. Now, if I have a 3D, I mean, if I look at it as a 3D problem, say, then that's something else. So you will have something like this in Calc 3, in fact. But for us, it's just single variable mathematics. So there is no y and z. It's just one direction, which I chose y for this direction of movement, say. So I have to find dv, the simplest dv that I can imagine, and then write that dv and just integrate. So that's all. Because the rho g and x are just rho g and x, and well, it's not x, sorry. I choose y, right? I use y, so let's write y. So my job, or a physicist's job, is simply writing down the dv. And in fact, that's why there's so much in depth of mathematicians, because that's mathematics. So I know, well, you say the formula comes from physics. So as a mathematician, I should find dv. So what do you think the best dv is? The best infinitesimal volume? Well, I suggest this. Why not as, well, let's say we are at height y. At this height, I pick a very small portion of water. So I just go down by dy. Well, this is exaggerated. I've exaggerated a lot. So, and do this. Well, okay. So, this is my dv. This is my dv. So let me pull it down here. So I'll draw that dv here. Well, let's draw it here. So my dv is something like this. And this is dy. And I need this. Fine. Why I'm just saying I need this? Because that dy is very small, infinitesimal. So I can assume that this is in fact a cylinder, right? I can assume that this is a cylinder. Right? Since dy is small, I can assume that it is a cylinder. So what do I need? I need this r, the radius. I need the radius as a function of what? You see, the radius changes with y. Up, down, the radius changes. The radius is something here, and there's another thing here. So the radius changes with y. So radius is in fact a function. Okay. So the dv, in fact, in this situation is simply r pi r squared dy. Pi r squared is the area of the base. Remember, volume of cylinder is area of the base times height. Area of the base is pi r squared, and the height is dy. That's it. So I have dv. I have dv, and I just plug in here and integrate. Since it's over y, I can just put, say, the origin here, for example, and it goes from 0 to h. Okay, so if origin is here and this is the positive direction, this becomes from 0 to h, say, if it is full. If it's full. Otherwise, it goes from 0 to somewhere here, h. What I'm saying. It is up to here, h1. And what do I have? I have a rho g, which I assume that it is fixed. Rho g is weight density. And then I have pi r squared dy, and outside I have y. Okay? So if I put the origin here, some students prefer this point to be the origin, okay? It depends on your choice. If I put it here, then this direction is positive, and this is in fact the y-axis, so I'm using y. And I said this small portion, this is my dv. dv is rho pi r squared dy. Pi r squared is this times dy. So that's the dv times rho g, that's the dm times y. So that is my work of the pump. Okay, so work of this pump, let me write it here more explicitly. It goes from 0, say, to h1, which is, well, height, this is filled up to h1. Then I have, well, let's write rho g outside. Rho g is fixed. If sometimes rho is not fixed, so you have to write rho inside. But anyway, let's assume it's fixed, and then it is pi r squared y dy. And r is a function of y. It's important. So what happens in the end? In the end, my job as a mathematician or physicist comes down to writing r as a function of y. So in the end, it comes down to simple high school geometry. You say, no, it's mathematics, blah, blah, blah. No, it's just simple high school geometry, you will see. Okay. So let me give you a concrete example here. And so let me erase all these things. So example is what I'm going to go. And well, let's say R is how big R could be in SI units. Let's say it is like, I don't know, like 5 meters. And H, how tall? Like 20, is it? So H is 20. And let's say it is full. Let's say it is full. Okay. So let's cut this way and look at it this way. Cut, look, and we have this. This is at the y side. So this distance is y. And let's say this is point O and G. Right. So this is y and this is h. This is h is 20, say, and this is in fact 5. And this is r. I should find r in terms of y. Now let's look at this triangle OH, say A, in triangle OHA. Let's write this A, say B and C here. I have this BC over HA equals OB over OH. Right? There is similarities of triangles, high school geometry. So BC is R, OH is 20, OB is 20 minus Y, and OH is 20. So if it's good to do this. No, this is fine. HA is fine. Yeah. So I can write this as divide this, so I have 1 minus y over 20. Now it's better to write it like this. So what is r then? R, let me write it here. R will be 5 times this. So R is 5 times that. And well, let's do rho G for in SI units is 1000. Well, let's just write rho G. I think it's 1,000. Anyway, so let's find some space here to write the integral. So work done will be rho G, integral from 0 to 20 is full, and the pi r is this thing, 5 times 1 minus y over 20 times another y dy. If you forget this y, what you are doing is you are finding the volume of this, the volume of water. So don't forget the y. Okay, so this is work. And the only thing is this rho G, which I can't find it here. I can check online and see what rho G is. I think that's 1,000. So that's 1,000. So this is 1,000. So I will have this integral. G, let's make it 1,000 pi. And I also can write this 5, the 5 can come out, and that gives me 5,000. 5,000 pi times y times this is y minus y squared over 20 dy. Well, I leave this to you to find, but that is in fact what happens. Okay. So that was the story of work, in fact, and I want to stop here because there's one small portion. Well, okay, let me continue and finish this because there's just one page is remaining, and that is average value of a function. So let me also do average value here and finish. I didn't know that I could finish today, and I will do more examples during the sessions. So average value is simple. So if I have that's average value of a function, in fact that is section 6.5. So that was 6.5 and that was 6.4. Yes. So average value is very simple. If I have a function, say from A to B, A, B. Right? So I ask this question. I have an area here. So the area is in fact AB fx dx. Remember? The simplest thing, that's the area. I say, okay, what is, can I find a number? Just a number, f average. F average. Such that when I multiply this f average by this distance, I will get the area. So the average is, say, if this is the average, say, well, let me make some changes here so I can. So average will be somewhere here, f average. And what I'm saying is that this this area, A, B, say C, D, for example. So the area of A, B, C, D equals area under the curve. Well, that definitely is not the average value, because then this shaded area and this shaded area should be the same, right? Because this area is between both of them, so it's shared between both of them. So it remains this one, and here this one and this one. So I guess this is not a good position for this average value. It should be a little higher than this. So let's move it higher. So this shaded area will be equal to this shaded area, this one and this one. So this is area 1, area 2, and this area 3. Then area 3 should be area 1 plus area 2. Right? Because this part is shared. This part is shared. Well, anyway, that is the picture. This picture is nice. So, F average times B minus A is this area, A, B, C, D. So F average will be 1 over B minus A integral. A is this, A, B, Fx dx. Okay. So that's it. That's simply average value of a function. It's just finding an integral and dividing by B minus A. Okay. So that was chapter 6, in fact, and I will do problems during the sessions. And we have another session on Thursday, so see you then.